So I wanted to go over a common misconception or maybe a clarification of what I mean by a product in what we're talking about right here. So the first idea is that Fn is not an algebra under dot product. And so the dot product takes two elements of Fn, and here, let me build it up. So you take the ith coordinate of u and the vth coordinate, the ith coordinate of v, and then you sum all these up through all the dimensions that you have. That's how it's defined. And then what that gives you is it gives you something from the scalar field, which in particular is not in Fn. So I guess to be precise here, I should say for n strictly greater than 1, because F is an algebra over itself in sort of the standard trivial way, but not for anything else. So for vectors in R2 or C3 or anything like that, it's not going to work. And then you might think, oh, well, what about cross product? Because if you're in F3, actually, is there such a thing as a complex cross product? Let's not mess with that for right now. Let's just stick with R3. This one's also not a cross product. Or sorry, not an algebra. Now, it is true that if you have two elements of R3, then U cross V is again going to be an element of R3, so it doesn't break down for that reason, but it's not associative. And so for an example of that, take something like here. If we take the standard unit basis I to be the vector 1, 0, 0, and j to be the vector 0, 1, 0, and k to be the vector 0, 0, 1, then if we look at I cross j, then the rule for the multiplication, the right-handed rule, tells you that this is going to be I times, and then I cross j evaluates to k, and then I cross k gives you minus j. But if you look at taking I cross I first, the cross product is something in terms of the sign between the angle of the two vectors. So if you have the same vector with itself, the sign is 0. So that's going to give you 0 cross j, which is just 0. And then these are clearly not the same. So these are not the same. So it fails associativity.